Please join me in welcoming to the Distinctive Voices podium Dr. Arthur Benjamin, the Mathemagician.
Thank you. Thank you. Well, good evening, ladies and gentlemen. My name is Art Benjamin, and I am a mathemagician. What that means is I combine my loves of math and magic to do something I call Mathemagics. But before I get started, I've got a quick question for the audience. By any chance, did anyone happen to bring with them this evening a calculator? Oh, I see a few. Good. Let's see. So if you have a calculator and you're pretty good at using it, raise your hand. Let me see. All right, so I see, I see 1 and 2 and, 3 and maybe one more. 4. Would the 4 of you join me up on stage, and let's give these volunteers a nice round of applause. Come on down. Great. All right. Let's see. Where did the other volunteers go? I see a calculator being passed around like a hot potato. Why don't you just join us? And maybe one more if anyone else would like to. In fact, anyone who doesn't have a calculator, I do. Would somebody else like to join our group? You don't get as many volunteers that way. Let's see. All right. What? You're pointing to somebody else? Okay. Great. Come on down. Let's give our volunteers a nice round of applause. Great. Awesome. There you go. Now, since I haven't had the chance to work with these calculators, in fact, why don't you all step up on stage right up here so everyone can see you? Since I haven't had the chance to work with these calculators, I need to make sure they are all working properly. Would somebody get us started by giving us a 2-digit number, please? How about a 2-digit number? 21. Great. And a 3-digit number. How about a 3-digit number? 365. Multiply 21 times 365. Make sure you get 7,665, or the calculators are not working. Are all of your calculators working? Give them a nice round of applause. Good. Now, I notice that took some of you just a little bit of time to get your answer. That's okay. I'll give you a shortcut for multiplying even faster on the calculator. There's something called the square of a number, which most of you know is taking a number and multiplying it by itself. For instance, 5 squared would be 25. Right. Now, the way we can square on most calculators, let me demonstrate on this one because I know it works, is by taking the numbers such as 5, pressing times, and then equals, and on many calculators that will give you the square. On these sophisticated ones, I think you have an x squared button that'll do it even faster. What I'm going to try and do now is to square in my head 4 2-digit numbers faster than they can do on their calculators, even using the shortcut method. What I'll ask is 4 people here in the second row, 1, 2, 3, 4, each yell out a 2-digit number, and if you would square the first number, the second, the third, and the fourth, I will try and race you to the answer. So, quickly, a 2-digit number, please. 89 squared, okay. 47, okay. 76, you say? Okay, one more. 17. Would you call out your answers, please? 7,921. 2,209. He's still working on it. Do 76 times 76, okay? While he's doing that, what did you get as your answer? 289. And finally, 5776. Let's give them a round of applause. Let me try to take this one step further. Going to try to square some 3-digit numbers this time. I won't even write these down. I'll just call them out as they're called out to me. Anyone at all call out a 3-digit number. Anyone on our panel verify the answer. If I get the answer right, give me a thumbs up. If I make a mistake, let me know, and I'll try and fix it. A 3-digit number, anyone? What was that? 129 squared is 16,641. 16641, good. Another 3-digit number, what was that? 462 is 213,444. 213444, good. How about another 3-digit number, sir? 758. 758, I think that's a hard one. 574,564, good. Another 3-digit number, please. 333 is 110,889. Yes, good. Another 3-digit number, please. Sir. 871 is 758,641. Good. One more 3-digit number.
Okay, 237.
237 is 56,169. Thank you very much. How's it going there? Let me try to take this one step further. I'm going to try to square a 4-digit number this time. Now, I'm not going to beat you to the answer on this one, but I will try to get the answer right. To make this a little bit more random, let's use 4 people here on the aisle. If I can get the first 4 of you to call out a single digit between 0 and 9, that will be the 4-digit number that I'll square. 5, 7, 8, 3. 5, 7, 8, 3. This will take me a little bit of time, so bear with me. 33,443,089. Thank you very much. Now, I would attempt to square a 5-digit number, and I can, but unfortunately, most calculators cannot. 8, what's that? Yours can? Let me see. I'll talk to you later. Forgot where I was. Yeah, I see. But since we've reached, I'll get back to you. Since we've reached the limits of some of our calculators, I'd like to conclude the first part of my show by trying something a little trickier. Let's take the last 3 digits of the number that was called out just now, 783. Would you each enter 783 on your calculator? And instead of squaring it this time, I'd like you to take that number and multiply it by any 4-digit number that you'd like. But don't tell me what you're multiplying by. Just multiply it by any random 4-digit number. So you should have as an answer either a 6-digit or possibly a 7-digit number. How many digits do you have in your answer there? 6 or 7? 7. 7? 7? 7. Is there any possible way that I could know what 7-digit numbers they have? Say no. Good. Then I shall attempt the impossible, or at least the improbable. What I'd like each of you to do is to call out for me any 6 of your 7 digits. Call out any 6 of them in any order you'd like. 1 digit at a time, I shall try and determine the digit you've left out. So starting with your 7-digit number, call out any 6 of them, please. Any order.
727244.
Did you leave out the number 1? Good. That's 1. You've got a 7-digit number. Call out any 6 of yours. They're right there, I hope. Are they still there? Or did they disappear? Okay, call out any 6 of them, please. Loud and clear. Or Dad can read them.
618018.
Did you leave out the number 3?
Yes.
Good. You've got a 7-digit number. Any 6 of them, loud and clear.
7277373.
I think you left out the number 7. Lots of 7s there, right? Good. That's 3. The odds of me getting all 4 of these by pure guessing would be 1 in 10,000, 10 to the 4th power. Okay, finally, you've got a 7-digit. Call out any 6 of them. Really scramble them up this time.
2, 4, 3, 5,
A little bit of trouble with this one. Do me a favor, if you would. Concentrate on the digit you left out. Doesn't do any good. It just looks dramatic. Did you leave out a 0? Because I was getting a lot of nothing. Okay, let's give all 4 of these people a nice round of applause. Thank you very much. Thank you. Well, for my next number, I'd like to present something we mathemagicians refer to as magic squares. They're kind of like Sudoku for magicians. Now, I have done such an extensive study on magic squares that I'd like to create one for all of you right before your very eyes. But for this, I'll need another assistant, someone here I do not know. And let's see. Okay, you're waving. What's your name? Allison. Let's give Allison a nice round of applause. Come up here, Allison. Allison, there's so many ways to spell. Is that Allison? Yeah. Okay, Allison, if you would stand right there. Now, you were so eager to participate. We have to make clear with the audience, have we ever met before? No. You seem proud of that fact. Okay, well, good. Allison, I'll ask you another question, and if it's too personal, I can change the question. Allison, are you willing to share with us your birthday, including the year? Yeah. Sure. Okay, Allison, what is your birthday? April 29, 4/29. 1997. 4/29/97. Allison, if we were to add the numbers in your birthday together, let's see, 4 plus 29 is 33, plus 9 is 42, plus 7 is 49, then 49 becomes your magic number. What I'm going to try and do now, Allison, is to fill out the rest of this box in such a way as to get your magic number appearing here as much as I possibly can. This will take me a couple of seconds, so bear with me. I think that works. Allison, would you choose for us any row? Row number 2, 3, or 4, which would you like? 3. Okay, class, together. 8 plus 10 is 18, plus 28 is 46, plus 3 is 49. The others were 4, 33, 42, 49, 8, 16, 19, 49, 29, 31, 40, 49. Would you choose a column, Allison? 1, 2, 3, or 4? 4. Okay, class. 7 plus 30 is 37. Plus 3 is 40. Plus 9 is 49. The others were 4, 12, 20, 49, 29, 37, 47, 49, 9, 12, 40, 49. How about that? Now, Allison, I'm not through with you. I decided that since this was your magic square based on your birthday, at no extra charge, I would give you these diagonals as well. Check it out here. 29 plus 10 is 39, plus 3 is 42, plus 7 is 49, 4, 12, 40, 49. But I didn't stop there either. I decided that since this was for Allison, wouldn't it be great if we could get these 4 in the center to add up as well? Check it out here. 8 plus 3 is 11, plus 28 is 39, plus 10 is 49. But did I stop there? No. Allison, you may have noticed I put a little extra attention in that corner. I did that so I could get these 4 squares. 4 plus 29 is 33, plus 8 is 41, plus 8 is 49 to add up. And I figured, heck, as long as we got that group of 4, let's have a party. We may as well get this group of 4, 9, 16, 46, 49, 8, 18, 20, 49, 28, 31, 40, 49. But did I stop there? No, I said Allison wouldn't be happy unless we got this group of 4, 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 this group of 4. Now, I have to apologize, Allison. I was not able to get this group of 4 nor that group of 4 to add up, but I had to do it that way if I was going to get these 4 in the corners. I knew that would be important to you. 4, 11, 20, 49. But wait, here's the cool part. Not only, Allison, do those 4 numbers in the corners add to 49. If you look at them closely, you'll see we have 4, 29, 97. I was able to give you your birthday a second time. I thought you'd like that. So please keep this as a souvenir from me, and let's all give Allison a nice round of applause. Thank you, Allison, very much. Speaking Speaking of birthdays, by any chance, does anyone here happen to know the day of the week that they were born on? If you think you know your actual birthday, raise your hand. All right, starting with this gentleman here. What year, if I may? 46. And what month? 1946. And what month? April what? 27. Was that a Saturday? No? It was a Saturday. Let me get back to you. Somebody else. Yes, sir, what year, sir? 52. And the month? November what? 22. Was that a Saturday? I must have gotten you two confused. Okay. 2 Saturdays in a row. What are the odds? Really, what are the odds? 1 in 49, but that's another talk. Okay. Another, yes, please. What year? And the month? January what? 8th. Was that a Sunday? Good. Who else? Yes, sir. What year? And the month? January what? 13th. Was that a Monday? I think so, too. How about you? What year? And the month? October what? 21st. Was that a Sunday? Yes. And how about one more? Yes. What year?
1973.
And the month? August what? 31st. Was that a Friday? Thank you very much. But let me get back to my original friend here. I do come prepared for these disagreements. I brought along with me a book of calendars. Goes as far back into the past as 1800, because you never know. I didn't mean to look at you, sir, when I said that. You were just sitting there. But if I can get one of you guys to help me out here. So let's go back to, you said it was at 1956? 46. Okay. So turn to the calendar with 1946. And the date was? April 27th, which I still believe is a Saturday. Can you confirm?
Yeah, Saturday.
Your mother lied to you. What can I tell you? As long as you have that book with you, do me a favor. Turn to a year outside of the 1900s, either in the 1800s or way into the 2000s. That'll be a much greater challenge for me. What year would you like, sir? 1865. A good year except for Lincoln. Okay. And what month? March what? 11th. Was that a Saturday?
Yes.
And it was cloudy, I think. Thank you very much. Thank you. In fact, anybody else who wants to know their birthday, see me after the show, and I will be more than happy to tell you. I'll be out in the lobby. Now, folks, if I were performing for a different kind of audience, say at the Magic Castle in Hollywood or Disneyland, as I have occasionally done, I would follow this up with other feats of magic and mind. But for an audience such as this one, so dedicated to the explanation of science and mathematics, I actually prefer to break the magician's rule and explain to you most of what you've seen me do up here and more. In fact, I'd like to conduct the rest of this program, the next 40 minutes or so, very informally. So feel free at any time to interrupt me with questions about anything at all. I mean, even if it has nothing to do with what I'm talking about, it's more interesting that way. But inevitably, the first question is, well, okay, start explaining how do you multiply numbers so quickly? So let me start with that one, and then I'll take your questions about anything at all. Now, I like to do everything by example. We'll start off small, and we'll work our way up to some big calculations. So give us a 2-digit number times a 1-digit number as our first problem. 42, let's make it bigger, times 7. Okay. Is 294, and here's how I do it. Now, if there's only one thing you remember from this entire presentation tonight, it should be this. I do all of my calculating from left to right. Now, that's the opposite of how we learn to do it on paper. On paper, most people go from right to left, which is fine for doing it on paper. But if you want to do the math in your head like I do, then I say you should do it from left to right. After all, we read numbers from left to right. We pronounce numbers from left to right. We say 42, not 2 and 40. And with just a little bit of practice, you can calculate from left to right even faster. Let me show you how. We start with 7 times 40, which is what? 280. And 7 times 2 is 14. Add those together from left to right, and we get 294. Now, it took me about a minute to explain that, but trust me, with just a little bit of practice, you can do any 2-digit times 1-digit number in just a few seconds. It's just a matter of practice. Let's go up a level, because I know this audience can handle it. Let's try a 3-digit number times a 1-digit number. Sir, how about a 3-digit number this time? 399 times a 1-digit number. 7 is 2,793. Now, I'll actually show you 2 ways of doing this problem. The way I normally do a problem, much like we do here, is I start at the left with 7 times 300, which is 2,100. Now, folks, here's another reason for doing this from left to right. At this point, I know that my answer is a little bit bigger than 2,000. Right? If I were doing the problem from right to left, all that I would know is that my answer ended in 3. And it's more important to know that you've got an answer that's a little bigger than 2,000 than to know that you have an answer that ends in 3. So by working from left to right, you're working with the most significant digits right from the start. Okay, giving you a better mental estimate of the answer. But let's get the exact answer anyway. Next, I do 7 times 90, which is 630. Now, at this point, ladies and gentlemen, I stop. Before I do 7 times 9, I stop to add these 2 numbers. So I have 2,100 plus 630 is 2,730. Finally, we do 7 times 9, which is 63. Add those together from left to right to get 2,793. Now, I know there were some of you in the audience, in fact, I see someone raising his hand already, says, wasn't there a much easier way of doing this problem? Exactly. And that's how I would take advantage of this special problem, right? For 399 times 7, we would do that, 399 times 7, as taking advantage of 399 as 400 minus 1, right? Do 7 times 400 is 2,800 minus 7 times 1, that's 7, to get 2,793. And that's, in fact, how I did that. But I don't always get quite so lucky, thank you. And when I don't, I go through the process like this. Trust me, with just a little bit of practice, you can do any 3-digit times 1-digit number in just a few seconds. But let me show you something that you can all learn to do right here, right now, that'll take you much less practice. Okay, you'll get very good at it very quickly. Something that you saw me do earlier tonight when you saw me squaring numbers, 2-digit numbers, 3-digit numbers, bigger numbers. Let me show you the method that I use for squaring 2-digit numbers. And if you're interested, just go ahead and ask me, and I'll show you how we can extend that to 3-digit and higher. Let's start off with a small 2-digit number. Sir, how about a 2-digit number just to start? Just give me a small 2-digit number. 11. Now, actually, 11 is a very special number. And in fact, rather than square 11, since you mentioned it, let me show you something that's great for kids. If I'm presenting for a group of elementary or middle school students, here's a way of not just squaring 11, but multiplying any number, any, say, 2-digit number by 11. Give us a small 2-digit number just to illustrate. 45 times 11 is as easy to do as 4 plus 5. 4 plus 5 is 9, and there's your answer, 495. I told you it was easy, right? All right. Yes, sir.
Is there another way to do that?
Well, actually, I don't think as easy as...
10% of the number will give you 11.
Yeah, I think 4 plus 5 is 9 is a little easier than that. But I'll tell you what. If you want to take this... So, okay, we'll do another one just to make sure. So, everybody, if the question was 81 times 11, what's the answer? 891. Now, before you get too excited, I've only shown you half of what you need to know. If the number adds up, what if the numbers add up to something bigger than 9? Suppose we had a problem like 85 times 11. Now 8 plus 5 is 13, but the answer is not 8, 13, 5. We only have room for the 3, but the 1 makes the 8 carry, and the answer is 935. You got it. So here, so for all of you, tell me, when I count to 3, when I say 3, and not before, tell me 77 times 11. 1, 2, 3. 847. Give yourselves a nice round of applause. Good job. Okay. But I digress. I said we would square two-digit numbers. Give us another two-digit number. 24. What was that? 24? Okay, 24. Now 24 is not a bad number to multiply, but what number close to 24 is much easier? 25. Most of you said 25, and that is easier, but even easier than that would be 20, because 20 ends in 0, and I like zeros. Okay, so I take 24 and I bring it down 4 to the round number 20. Now, whatever comes up must come down. If I go down 4 to 20, I balance that by going up the same distance to the number 28. So the first part of my calculation is I do 20 times 28, which is, of course, just 2 times 28 with a friendly 0 attached. 2 times 28 from left to right is 56. So 20 times 28 is 560. Almost done. All we have to add to this is the square of the number we went up and down. We went up and down 4. 4 squared is 16, and there's your answer, 576. Let me do a couple more of these just because I want to make sure you leave tonight pretty good at doing them. How about another two-digit number, please? Or sir, how about you? 43. Okay, so this time the nearest easy number would be 40. So I'll go down 3 to 40. Therefore, I go up to what number? 46. Okay. Now let's do 40 times 46 together. Actually, let's just do 4 times 46, and we'll attach the 0 when we're done. 4 times 40, everybody, is 160. 4 times 6 is, say it, 24. Okay, 160 plus 24 from left to right is 184. Good. With the friendly 0, that's 1,840. And what do we add to that? Yeah, the square of 3, which is 9, to get 1,849. Okay? Now, it also works if you go up to the nearest number. I mean, so, for example, I wouldn't actually do it this way, but let me just show you. If you took 43 and you said, well, 40 is a nice number, but 50 is even nicer, you could go up 7 to 50, then down 7 to what? 36. One way of getting 36 without doing the subtraction, maybe you think this is harder, but I don't, is if you doubled 43, you get 86. And if this number is 50, this has to be 36, because they have to balance. They have to add up to twice that. I find that easier, but you might not. Okay, anyway. So 50 times 36. Now, you could do 5 times 36 and attach a 0, or you could, if you like division, say, well, 50 is half of 100. What's half of 36? 18. So you get 1,800. Okay, whatever. What do we add to this now? We always add. What do we add to this? The square of 7, which is 49. And there you have it, 1,849. The same as this side. Now, I don't know about you, but when I do these kinds of problems, when I did these problems as a kid, and I still do these as an adult, I think it's kind of cool that you could take a problem, do it lots and lots of different ways, and if you're careful, you'll always come up with the same answer. I found that consistency of mathematics as a kid, I found it to be absolutely fascinating, and I still do as an adult, as a professional mathematician. Okay, now it's your turn. I'm going to give somebody here an opportunity to show off and win a prize. So I have with me my book, Secrets of Mental Math, and thank you, and And so I'll give it to the first person who can do this next problem, although it's probably the person who least needs the book, but we'll do it that way anyway. I should give it to the last person in the audience to get the answer, right? But anyway, that would take too long. All right, so when you think you have the answer, raise your hand, okay? But no talking, no whispering, and especially no calculators. Don't even do it on paper. Try and do it in your head, all right? So the first person who can square the number 97. 97. Think of what you'll go up to. Think of what you'll go down to. And what you'll add. All right, I think I saw your hand go up first. What did you get? Not quite. No. What did you get? No, not quite. Not quite. On the aisle, what did you get? 9,409. Give him a nice round of applause. And no, and let's just, sir, would you come on down and deliver that book to the gentleman there? I appreciate it. All right, so what you did, there you go. Whoops. I end up dropping it anyway. All right. What you did, I hope, was you went up 3 to 100, down 3 to 94. 94 times 100 is 9,400, plus the square of 3, which is 9, to get 9,409. Good job. Okay, well, as I said, I have hours and hours of stuff that I can show off to you, but less than a half hour left here. And I want to spend that time answering questions and talking about those things that are of interest to you. So for the rest of this time, Q&A, I'm here to answer whatever it is that you are interested in. So what would you like to know? Yes, please. What's your question? When was my first recollection of being interested in math? It was probably earlier than I have recollections. That is, my mother says that even as 2, 3 years old, I enjoyed playing with numbers and finding little patterns and building patterns. My mom says, and I don't remember this, but she says this, that I said as a kid, I asked her, do 2 squares make a rectangle? And she said yes, which isn't entirely true, but, yeah, if they're the same size. And then I said, but 2 rectangles don't make a square. And so that, to me, was an indication of someone who liked to think mathematically. So that's as far. But I didn't come out, squaring numbers like that. This was a very gradually acquired skill, for fun. Yes, sir.
There have been people throughout history who have been able to do these so-called magic feats. Did you learn your methods from what those people had written, or did you develop them independently?
So the question was most of what I'm doing, was it self-taught, or did I learn this from other books like the one I presented? And most of it, nearly all of it, was self-taught. Now, nearly everything I do had been discovered by people centuries ago. It's based on nothing more than the most basic of algebra, but I had the pleasure of discovering these things for myself. In fact, if you'll permit me, let me tell you the story of how I developed this method of squaring. I mean, anyone who's had algebra would say, oh, you're squaring the number a. You take a plus some distance times a minus the same distance and add the square of the distance. And if you multiply these things and do the algebra, you get a squared. Okay. But that's not how I did it. I didn't know my algebra well enough to do it that way. Here's how it came to me. I remember it was in 8th grade, and I was taking a bus downtown Cleveland, where my father worked, and I was like many an 8th grader, my thoughts turned to numbers that added up to 20. And I said, I wonder how big two numbers could multiply if they had to add up to 20. So I said it's probably the middle numbers, right? Probably taking 10 times 10 gives you 100, and I don't think you could do any higher than that. But how do you know? Well, we'll test a few others. So I did 9 times 11, got 99, which was almost 100, but it was shy by 1. Then I tried 8 times 12, got 96, and that was almost 100, but that was shy by 4. And 7 times 13 was 91, still is, and that was shy by 9, and 6 times 14 is 84, and 5 times 15 was 75. And I noticed two things. I noticed, first of all, hey, as these numbers get farther apart, the product gets smaller. And how small were they from the big number? They were 1, 4, 9, 16 away, 25 away. Squares, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. That's really cool. I wonder if that always works. So how can you tell if something's always going to work? You try another example, right? So we say, okay, let's try numbers that add up to 26 instead. So I start in the middle with 13 times 13 and got 169. 12 times 14 is 168. 11, I wasn't doing it as quickly back then, but I just did the multiplications, and I saw the same pattern. Hey, those numbers are getting smaller, and look how far they are from 169. 1, 4, 9, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. And then it dawned on me, maybe one of the most creative ideas I've ever had in my life was I said, you could take advantage of this pattern. Suppose you wanted to do 13 times 13. Instead of doing this hard problem, let's do this easier problem, 10 times 16, because it's much easier to multiply by 10. And then your answer would be small, but you'd add back the square of the distance, 3 squared. So anyway, as luck would have it, a few weeks later, I'm sitting in my algebra class, and our algebra teacher leaves an answer on the board as 108 squared. It was the answer to some long algebra problem. And I blurted out, well, that's 11,664. And she said, yes, how did you do that? I said, it's easy. I went down 8 to 100, up 8 to 116, multiplied them to get 11,600 plus the square of 864, 11,664. And she said, that's right. And now she instantly recognized the algebra. She knew what was going on. And I showed it to her, and she had never seen that method before. So I got very excited, thoughts of Benjamin's theorem. I'm going to be famous. This is great. But it was the first time it dawned on me that I'd figured something out that wasn't going to be taught to us in school. And that really got me even more excited about mathematics and gave me the incentive to do bigger problems and do them even faster. So anyway, long answer to your question. And as a result, I would study. I would look to find other ways of doing things. A few years later, I saw this same method written up in a book by Martin Gardner, and it ruined my day. For years, I thought I had figured out. But anyway, other questions? Way in the back, sir.
Yes. How in the world can you ascertain birthdays back in the 1900s?
Yeah. So how to figure out birthdays? I'll tell you what. I normally don't go into the details, but I will do that for you because I know this is an audience that can handle it. In a sentence, it's mathematical. Okay, the calendar is a very mathematical object and has a pattern that can be exploited. Let me start by showing you how to figure out the day of the week for any date this year, for 2009. And then I'll show you how to do it for next year, and then as far into the future as you want. And then if you're still interested, I can tell you how to go back in time as well. Every year gets a code number, and the code number for 2009 just happens to be 4. Okay? Just trust me on that. Next, every day of the week gets a code number, Monday, Tuesday, Wednesday. And the code numbers for those are 1, 2, 3, 4, 5, 6, and Sunday is 7 or 0. And I like doing, actually the code that I learned years ago had the numbers differently, but I've rearranged it to suit the 2000s and to suit the fact that by doing it this way, Tuesday is Tuesday, right? It's much easier that way, trust me. So Monday is one day. Tuesday is Tuesday. Wednesday, put the W on your fingers, there's the 3. Thursday is 4's day. Friday is 5 day. Saturday is 6er day. Sunday is 7 day. Or Sunday is none day. Or if you're Catholic, Sunday is none day. Okay. Whatever. Then we need a code for every day, every month. And this is the only hard part, the part that requires some study to memorize. And the codes for those are 622, 503, 514, 624. I know there are even mnemonics, memory tricks for learning this list. I mean, you could find, but why this works, I'll get into in a minute. But let's do how before why. All right, so now that you have this, once you know this, you can now figure out the day of the week for any date this year. So somebody give me a birth date, and we'll figure out its day of the week for this year. What date would you like? February 7th, 2009. Okay, here we go. So February has a month code of 2. All right. The 7th, we simply add 7. Plus 2009, for that we add 4, because I said so. Okay. Add those 3 numbers together, and we get 13. Now, if you wanted to, you could count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 until you get to 13, but you don't have to do that because every 7 days the week repeats. So you could subtract any multiple of 7, and that's not going to change its day of the week. So I'll subtract 7, giving me 6, and 6er day is Saturday, so the date you gave me this year was on Saturday. Okay? So one more example. Somebody give me another date, just so we all have it. What was that? October 12th. Okay, so October 12th, 2009. October has a month code of 6. Okay. For the 12th, we add 12. For 2009, we add 4. Add those together and we get 22. And now what's the biggest multiple of 7 I can subtract here? 21. So I subtract 21 to get 1, and one day is Monday. So that birth date will be on Monday. Okay, so you now know how to do this year, which is practical, right? It's not every day someone asks you for a date in 1926, but it is pretty every day that somebody asks for a date of some kind. Now, that's 2009, but what about next year? What about 2010? Well, what normally happens to your birthday as you go from one year to the next? It goes up a day. Why? Because usually there are 365 days between your birthday, and 364 is a multiple of 7. 7 times 52. So if every year had 364 days, your birthday would be on the same day each year. That would be boring, and that's why they don't do it that way. And something about the earth and the sun, right? So with 365 days, all we have to do is bump up by a day. So for 2010, all we have to do is change the year code from 4 to 5, and everything else stays the same. For 2011, the year code would be 6. But for 2012, now that's a leap year, right? Every multiple of 4, so that's a leap year. So we have to leap over the 7 to get an 8. So the year code for 2012 could be 8. But since I'm going to subtract 7s when I'm done with everything, I'll just bring that number down to 1 anyway. If you follow the logic here, you know that I have to make one correction if it was a January or February leap year. And I'll just put that here for those taking notes. In January or February leap year, you've added 1 too much. So I adjust the month code by 1. Anyway, with that, you can go as far into the future as you want. To go back into the past, it's based on the fact that 2000 has a year code of 0. 1900 gets a year code of 1. Combining these two facts, you can figure out any date. I'm not going to go into any more details on that, but I will say, if you're interested in learning those details, maybe this is the best time to do it, you can learn that in my Mathemagic course, which I will have available outside in the lobby afterwards. Forgive this commercial. It's 4 discs, 3 DVDs, and an audio disc. It's got everything I know about mental calculation, addition, subtraction, multiplication, divisions, the birthdays, the magic squares, the missing digit trick. All that stuff is here. It also comes with my book, The Secrets of Mental Math. You get all that. It's $40, and I take cash, check, or credit card. Okay, so as long as I'm embarrassing myself, I'll mention 2 other things that I also brought with me. Very recently, I put together some courses for a company called The Teaching Company. Do any of you get their courses? So 2 years ago, I put out a course called The Joy of Mathematics. It's 24 lectures on basically pre-college mathematics, everything from the joy of numbers up through the joy of calculus, the joy of Fibonacci numbers, prime numbers, algebra, probability, Pascal's triangle, imaginary numbers. Anyway, the Teaching Company normally it's 24 lectures, half hour each given by me. They normally sell these for over $200. I have them, again, out in the lobby for $60. I also have brought with me just this month, hot off the presses, my second course for the Teaching Company. And this one is on the area of mathematics known as discrete mathematics. That's my area of research. It is like a first-year college course. If you know, only prerequisites are algebra, but it's the mathematics that underlies computer science. That's also $60. If you're interested, see me after the show. The last commercial I want to do while I'm in commercial mode isn't for me, but instead is for my college. Whenever I speak before a group, especially a distinguished group like this one, they love for me to mention their name. So I'm going to do that now. I teach at a school called Harvey Mudd College. Let's hear it for Harvey Mudd. I know we got at least some alums out in the audience here. That's right. Harvey Mudd College, it's in Claremont, not far from here. 750 students, all undergraduates. All of them major in math, science, and engineering. About 40% of them enter Ph.D. programs when they finish. And 1/3 of their coursework is in the humanities, social sciences, and the arts. So not only are these students strong technically, they also understand the impact their work has on society. And I feel very, very privileged to be able to teach these bright minds. Okay, a couple more questions. Yes, sir?
Would you like to tell the audience about the number 1729 and the story behind it?
So lots of numbers have lots of pretty beautiful properties, and it's funny, if you're a singer, they might say, sing that song of yours. We love hearing that one. He says, tell us about the number 1729. Kind of gives you a new interpretation of, for my next number, we'll do 1729. So 1729 has any mathematician knows the story behind this. One of the most brilliant mathematical minds to ever walk the planet was an Indian mathematician by the name of Ramanujan. Self-taught genius. And almost went undiscovered. but sent his work to a few leading mathematicians in Europe, and one of them, a fellow by the name of G.H. Hardy, took his communications seriously enough, brought him to England. They published some of the most original mathematical work in the area of number theory that's ever happened. Well, as a story that illustrates Ramanujan's brilliance, when one day when Hardy visited Ramanujan while he was in the hospital, they were making small talk, and Hardy said, the taxi cab on the way to the hospital, the number was 1729, and I couldn't think of anything interesting about that number. That's what mathematicians talk about, And Ramanujan said, "No, Hardy, that's a very interesting number. It is the first number, the smallest positive number, that is the sum of the cubes of two positive numbers in two different ways." It's 10 cubed plus 9 cubed. It also happens to be 12 cubed plus 1 cubed. So the fact that this is equal to these two things isn't so remarkable as the fact that Ramanujan just spontaneously recognized this property. So that's a classic story, and a true story. Yes, please.
I wonder, do they even allow you in the casinos?
Do they allow me in the casinos? Not every casino knows me. So a few years ago, I taught a course at Harvey Mudd College in the mathematics of games and gambling, and including, how to count cards in blackjack, because it's really not hard. It's just boring more than anything. And I'm happy to say that some of those students, over their spring break, decided to go to Las Vegas, and they considered it the lab portion of the course. And a couple of them were kindly asked to stop playing because they were doing so well. So my best game is actually backgammon, and if anyone wants to play me, see me after the show. Yes, sir.
How would a presentation of yours at Magic Castle differ from your speech tonight?
How would my...
And do you have an example of how that might differ?
Well, what's interesting is his question was, how would my presentation here differ from my presentation at the Magic Castle? In a word, shorter. My presentation at the castle is all show and no tell. What you are seeing is, it's like going behind the curtain at the castle and learning the secrets behind the magic that I do. I also do card tricks and other things, but not at the castle, because I think if you're presenting at the Magic Castle, the audience, everyone in the audience is either a magician or a guest of a magician. In fact, anybody who purchases one of my courses, I will give you a guest pass to the Magic Castle, so you can go if you so desire. I will be performing there. You don't have to use the guest pass for this, but I will be performing there the week of Christmas, so December 21st to the 27th. The magicians work a full week, Monday to Sunday, and I'll be one of the 5 or 6 different magic acts appearing that week. So basically, I just don't tell them how I do it there. I'm just entertaining them. Other questions? Yes, please.
Other than in Vegas, give me some practical applications of this knowledge.
What are some practical applications of mental calculation? I most practically used it in the game of backgammon, where you have to be able to calculate probabilities quickly and count pips quickly to be good. More practically, I think people who are stock traders, day traders, are on the floor needing to be able to make very quick buy and sell decisions. I think as a profession, it's probably stock traders who are the fastest at rapid calculation. And I think it's a great thing for kids to learn doing mental calculations, because it, I think, improves their number sense ability. Now, speaking of kids, I have two kids, two daughters, Laurel and how do I want to say this? My wife, who also has training in mathematics, and it was a concern when we had kids that we might give them mathematical names. You know, if it was a boy, add 'em. If it was a girl, subtract 'em. You know, something like that. Luckily, we didn't. And my kids like math, I'm happy to say. And one of my daughters actually came with me tonight, and she wanted to make a grand appearance for you. So if she's still awake, Ariel, would you join us, please? Now, Ariel, though she loves numbers, also loves words. She loves memorizing things. And one thing that she's been doing for a little while is she can say the states in alphabetical order, and sometimes she can do it in under 30 seconds. Ariel, are you willing to give that a try? You see the clock there? All right, we'll wait till it gets to the 40. And when it gets to the 40, you go. Ready? Set? Go!
Alabama, Alaska, Arizona, Arkansas, California, Colorado, Connecticut, Delaware, Florida, Georgia, Hawaii, and Louisiana. Iowa, Kansas, Kentucky, Louisiana, Maine, Maryland, Massachusetts, Michigan. Minnesota, Mississippi, Missouri, Montana, Nebraska, Nevada. New Hampshire, New Jersey, New Mexico, New York, North Carolina, North Dakota, Ohio, Oklahoma, Oregon, Pennsylvania, Rhode Island, South Carolina, South Dakota, Tennessee, Texas, Utah, Vermont, Virginia, Washington, West Virginia, Wisconsin, Wyoming.
29 seconds! Thank you. You can sit down now if you'd like. Do a cartwheel. Well, I'll tell you what, folks, before we're nearly the end of time, I will gladly stay out in the outside in the lobby and answer more of your questions. But the last thing I want to do for you is to allude to something to do something we alluded to earlier when I mostly had 8-digit calculators on stage, but there was at least one person who had a 10-digit calculator. Two of you, okay. If you've got such a calculator, bring it out. The last thing I want to try is to square a 5-digit number requiring a 10-digit calculator. But to make my job more interesting for you as well as for me, I'm going to do this last problem thinking out loud. So you can actually, honestly hear what's going on in my mind while I do a calculation of this size. Now let's create a 5-digit number. How about we go up this aisle here? If I can get the first 5 of you to call out a single digit, that will be my 5-digit number. 7. Pick a number. 3. 5. 7. 76,357 squared. Yuck. Might even be prime. Let me explain to you how I'm going to attempt this problem. I'm going to break the problem down into 3 parts. I'll do 76,000 squared plus 357 squared plus 76,000 times 357 times 2. Add all those numbers together, and with any luck, arrive at the answer. Now let me recap. Thank you. While I explain something else. As I do this calculation, you might hear certain words as opposed to numbers creep into the calculation. Let me explain what that is. This is a phonetic code, a mnemonic device that I use that allows me to convert numbers into words. I store them as words and later on retrieve them as numbers. I know it sounds complicated. It's not. I just don't want you to think you're seeing something out of Rain Man here. There's definitely a method to my madness. Definitely. Sorry. One last instruction for my judges with calculators. Now, you should have a 10-digit answer, probably begins with a 5, ends with a 9. In between, I don't know. There's at least a 50% chance that I'll make a mistake somewhere in between. If I do, don't tell me what the mistake is. Just say you're close or something, and I'll try and figure it out, which can be pretty entertaining in itself. If, however, I am right, whatever you do, don't keep it to yourselves. Make sure everybody knows that I got the answer right, because this is my big finish, okay? So, without any more stalling, here we go. I'll start the problem in the middle with 76 times 357. 357 is 51 times 7. I'll take advantage of that. Now, 51 times 76 is 3,876. Times 7 is 26,600 plus 532 is 27,132. Double that to get 54,264. 54,264 becomes lure nature. Lure nature. That seems right. I'll go on. Lure nature. Okay. Next, I do 76 squared, which is 5776. So I can say 5 billion. Take the 776, add that to lure. 776 plus 54 is 830 million. Nature, nature. Okay, finally we do 357 squared. That's 400 times 314 plus 43 squared. It's 125,600 plus 1,849 is 127,449. Re-rope if I need it. Re-rope. Take the 127, add that to nature to get 391,449. Yes! Good! Thank you very much. I hope you enjoyed Mathemagic. Thank you. You want to take a bow with me?
Please, let's give Dr. Benjamin another round of applause and join us outside.